Sugar's journey begins far from machines and factories, in open fields where sugarcane grows slowly under the influence of sun, soil, and water. These fields are carefully selected, often located in warm tropical and subtropical regions where long hours of sunlight and consistent rainfall create the perfect environment for cane to thrive. Sugarcane is not a quick crop. It takes many months to mature, during which the plant steadily converts sunlight into stored sweetness. Inside each tall stalk, sucrose accumulates within fibrous cells, protected by a tough outer skin designed to withstand wind, heat, and heavy rain. Farmers closely monitor the growth cycle because timing directly affects sugar yield. If harvested too early, the cane lacks sufficient sucrose. If left too long, the sugar content can begin to decline as the plant uses its stored energy to support new growth. Soil health plays an equally important role. Nutrient-rich earth supports thicker stalks and higher juice concentration, while proper drainage prevents root damage. Irrigation systems are carefully managed to provide steady moisture without oversaturation, ensuring consistent growth across entire fields. As harvest season approaches, fields transform into zones of intense activity. In many modern farming regions, large harvesting machines move in straight, efficient paths, cutting cane close to the ground where sugar concentration is highest. These machines strip away excess leaves, chop stalks into sections, and load them directly onto transport vehicles. The process is fast and precise, designed to handle massive volumes of cane in a short time. In contrast, some regions still rely on skilled manual labor, where workers use sharp blades to cut and bundle cane by hand. This method demands strength, accuracy, and experience, as clean cuts help preserve juice quality and reduce contamination. Once cut, sugarcane becomes highly time-sensitive. The moment it leaves the soil, natural enzymes and microorganisms begin breaking down sucrose. This means delays can directly reduce the amount of recoverable sugar. For this reason, harvested cane is transported to factories as quickly as possible. Trucks loaded with green, freshly cut stalks form long lines moving steadily toward processing plants. The speed of this journey is carefully planned, often coordinated down to the hour. Environmental conditions during transport also matter. Excessive heat can accelerate sugar loss, while rain can introduce unwanted moisture and debris. Many producers schedule harvesting during cooler parts of the day or night to preserve sugar quality. Covered trucks or strategic routing may be used to minimize exposure and reduce delays. Even before the cane reaches the factory, quality assessment begins. Visual inspection helps identify damaged or dry stalks, while weight measurements give early indicators of yield potential. Every decision at this stage influences the efficiency of the entire process that follows. A well-managed harvest results in higher extraction rates, lower energy use, and cleaner juice during processing. The fields themselves represent a balance between nature and planning. Crop rotation, soil recovery, and sustainable farming practices are increasingly important to maintain long-term productivity. Farmers often return organic byproducts from the factory back to the land as fertilizer, closing the loop between field and factory. This relationship ensures that future harvests remain strong and consistent. At its core, the beginning of sugar production is a story of patience and precision. From the slow growth of cane under the sun to the carefully timed harvest, every step is designed to protect the sweetness stored inside each stalk. The quality of the final crystal is already being shaped long before machinery ever touches the cane, influenced by weather patterns, farming decisions, and the exact moment the crop is cut and moved toward processing, where the freshly harvested cane continues its journey, still carrying the warmth of the field and the potential locked within its fibers. Once sugarcane arrives at the factory, the focus shifts from agriculture to industrial precision, where speed and efficiency determine how much sweetness can be recovered from every stalk. Trucks unload their cargo onto large receiving platforms, and almost immediately the cane is drawn into the plant by powerful conveyor systems. At this stage, the cane still carries traces of soil, dry leaves, and other field debris that must be removed before processing can begin. Cleaning systems shake, spray, and rinse the cane, ensuring that only plant material continues forward while unwanted matter is discarded. After cleaning, the cane moves into preparation units designed to open its tough outer structure. Heavy-duty knives and shredders cut the stalks into smaller fragments, tearing apart fibrous layers that protect the juice inside. This step is critical because intact fibers trap sugar, reducing extraction efficiency. As the cane is shredded, its surface area increases dramatically, allowing later machines to access the juice more effectively. The process is loud and continuous, with steel components working in constant rhythm to keep material flowing without interruption. The prepared cane then enters the extraction section, where massive roller mills apply intense pressure. These rollers are among the largest and strongest machines in the factory, built to withstand constant force and heavy loads. As the shredded cane passes between them, the fibers are compressed and sugar-rich juice is squeezed out. Channels beneath the rollers collect this liquid, guiding it onward for purification. To maximize sugar recovery, hot water is sprayed onto the crushed cane between milling stages. This washing process dissolves additional sucrose trapped in the fibers, ensuring that very little sweetness is left behind. Extraction does not happen in a single step. The cane typically passes through multiple sets of rollers, each one removing more juice than the last. With every pass, the fibers become drier and lighter. By the final stage, nearly all usable juice has been extracted, leaving behind a fibrous residue known as bagasse. Although it appears to be waste, bagasse is one of the factory's most valuable resources. Conveyors carry bagasse directly to the boiler house, where it is used as fuel. When burned, bagasse produces large amounts of heat, which is converted into steam. This steam drives turbines that generate electricity and provides thermal energy for other processes within the factory. In many sugar plants, bagasse supplies enough energy to power the entire operation, reducing dependence on external fuels and lowering production costs. This efficient reuse of byproducts turns what could be waste into a vital energy source. The integration of energy production into the sugar-making process highlights the factory's design efficiency. Steam generated from bagasse not only powers turbines, but is also reused in heating stages, such as juice evaporation. Excess electricity may even be exported to nearby communities, making the sugar factory an energy contributor as well as a food producer. This closed-loop system reduces environmental impact and improves sustainability. Throughout the extraction stage, operators continuously monitor machine performance. Sensors measure pressure, temperature, and flow rates, ensuring that the rollers apply just the right amount of force. Too little pressure leaves sugar behind, while too much can damage equipment or release unwanted plant compounds. Regular maintenance keeps the machinery running smoothly, as even minor mechanical issues can disrupt the entire production line. By the time the juice leaves the extraction area, it has already undergone one of the most physically demanding stages of its journey. What began as rigid, fibrous stalks has been reduced to liquid and fuel, separated through force and careful engineering. This stage defines the efficiency of the entire factory, as every drop of recovered juice represents sugar that will later become crystal, while every fiber of bagasse burned helps power the next steps in the transformation process. After extraction, the sugarcane juice enters a phase where cleanliness and control become more important than force. The liquid collected from the mills is rich in sucrose, but also contains a wide range of impurities, including plant fibers, soil particles, waxes, proteins, and natural acids. Its appearance is dark and cloudy, far removed from the clear crystals it will eventually become. To move forward, the juice must be stabilized and purified, beginning with controlled heating that prepares it for chemical treatment and prevents unwanted microbial activity. As the juice is heated, lime is added in carefully measured amounts. This adjustment of acidity is a delicate balance, as too little lime leaves impurities suspended, while too much can damage sugar quality. The lime reacts with natural acids and causes fine particles to bind together into larger clusters. In some processes, additional agents such as carbon dioxide or phosphoric compounds are introduced to improve clarification, depending on the factory's technology and the desired final product. These reactions transform invisible contaminants into visible matter that can be separated. The treated juice flows into large clarification tanks, where time and gravity take over. Inside these tanks, the liquid slows and becomes still, allowing heavier impurities to settle at the bottom. Over time, a thick layer of sludge forms, composed of trapped solids and reaction byproducts. At the same time, clearer juice rises to the top, gradually changing color from murky brown to a lighter, translucent shade. Mechanical scrapers move slowly along the bottom of the tanks, collecting the settled material, without disturbing the clarified liquid above. This sludge, often referred to as mud, still contains traces of sugar. Rather than discarding it, factories send it through filtration systems to recover any remaining juice. The recovered liquid is returned to the main process, while the filtered solids are usually repurposed as agricultural fertilizer. This practice not only reduces waste, but also returns nutrients to the fields where sugarcane is grown, reinforcing the connection between farming and processing. Once clarified, the juice is significantly cleaner, but still contains a large amount of water. To concentrate the sugar, evaporation becomes the next focus. The juice passes into a series of evaporators, each operating under controlled pressure and temperature. As heat is applied, water begins to boil away as steam, leaving behind a thicker solution. These evaporators are arranged in multiple stages, allowing steam produced in one unit to heat the next, a design that conserves energy and improves overall efficiency. As evaporation continues, the liquid grows denser and darker, gradually transforming into a rich, golden syrup. Operators monitor this stage closely, measuring concentration and temperature to ensure consistency. If evaporation proceeds too quickly, the syrup may scorch or develop unwanted flavors. If too slow, energy efficiency declines and throughput suffers. Maintaining balance is essential to preserve sugar quality and maximize yield. This concentrated syrup represents a turning point in the process. While it is still liquid, it now contains a high level of dissolved sugar, bringing it close to the point where crystals can form. The removal of excess water not only prepares the syrup for crystallization, but also stabilizes it, reducing the risk of microbial growth and chemical degradation. Throughout purification and concentration, quality control remains constant. Samples are taken regularly to assess clarity, color, and sugar content. Adjustments are made in real time, ensuring that variations in cane quality or operating conditions do not compromise the final product. What emerges from this stage is a clean, concentrated syrup, carrying the essence of the original plant in a refined form, ready to undergo the precise conditions that will turn dissolved sweetness into solid crystal structure. With the syrup now thick, clean, and rich in dissolved sugar, the process enters its most delicate and closely controlled phase, where liquid sweetness is transformed into solid form. This transformation relies not on force, but on precision. The concentrated syrup is fed into large sealed vessels, known as vacuum pans, where pressure is carefully reduced. Lowering the pressure allows the syrup to boil at lower temperatures, preventing the sugar from burning or darkening and preserving its natural quality. Inside the vacuum pan, the syrup is heated gently while being continuously circulated. Sensors monitor temperature, pressure, and concentration with extreme accuracy. As water continues to evaporate under vacuum conditions, the syrup becomes supersaturated, meaning it contains more dissolved sugar than it can normally hold at that temperature. This unstable state is necessary for crystal formation, but must be maintained carefully to avoid uncontrolled crystallization. At the exact moment when conditions are right, tiny seed crystals are introduced into the syrup. These microscopic particles act as anchors, giving sugar molecules a surface to attach to. Without these seeds, crystallization could occur randomly, producing uneven or unwanted crystal sizes. Once the seeds are added, dissolved sugar molecules begin to align themselves around each crystal, gradually building solid structures one layer at a time. As the mixture circulates, crystals grow slowly and uniformly. Operators adjust temperature and pressure to control growth speed, as rapid crystallization can produce fragile or irregular crystals, while overly slow growth reduces efficiency. The thick mixture that forms, known as maskwhite, contains a suspension of sugar crystals within remaining liquid syrup. The appearance of the maskwhite changes noticeably as crystals increase in size, becoming heavier and more visible. When the crystals reach their target size, the maskwhite is discharged from the vacuum pan and transferred to centrifuges. These machines spin at very high speeds, using centrifugal force to separate solids from liquids. As the centrifuge accelerates, the heavier sugar crystals are forced outward against a perforated wall, while the liquid portion, known as molasses, is pushed through small openings and collected separately. During centrifugation, the separation happens rapidly and efficiently. However, the crystals that remain still carry a thin coating of syrup on their surface. To remove this layer, hot water or steam is sprayed into the spinning centrifuge. This washing process dissolves and removes residual syrup, improving crystal purity and brightness. The wash water is carefully controlled to prevent sugar loss while achieving maximum cleanliness. The expelled molasses is far from waste. It still contains dissolved sugar and valuable compounds. Depending on the factory's setup, molasses may be processed further to extract additional sugar, blended into animal feed, or used in fermentation industries such as ethanol and yeast production. This ensures that nearly every component of the original juice is utilized. As centrifugation completes, the now separated sugar crystals exit the machines and move onward in a free-flowing form. Their texture is coarse and granular, and their color depends on how much refining has taken place. At this point, the sugar is structurally complete, having transitioned fully from liquid to solid through controlled crystallization and mechanical separation. This stage represents a balance between chemistry and mechanics, where microscopic molecular behavior determines the macroscopic properties of the final product. Crystal size, strength, and purity are all shaped here, influenced by subtle adjustments in temperature, pressure, and timing. The success of this phase ensures that the sugar will flow smoothly, dissolve predictably, and meet quality standards as it continues toward drying, finishing, and eventual use in kitchens and industries around the world. After separation, the sugar crystals move into the final stages where stability, purity, and presentation are perfected. Although the crystals are now solid, they still contain traces of surface moisture that must be removed to ensure long-term quality. The sugar is conveyed into large drying systems, where carefully controlled streams of warm air pass through the moving crystals. This airflow evaporates remaining moisture without melting or damaging the crystal structure. Temperature and air velocity are precisely regulated, as excessive heat can cause discoloration or cracking, while insufficient drying can lead to clumping during storage. As the crystals tumble and move through dryers, they gradually become free-flowing and dry to the touch. This step gives sugar its familiar sparkling appearance and ensures it remains stable in varying climates. Once drying is complete, the sugar passes through cooling systems that lower its temperature to match ambient conditions. Cooling is essential because warm sugar can attract moisture from the air, undoing the benefits of drying and causing condensation inside storage containers. After cooling, the sugar is screened to achieve uniform crystal size. Vibrating sieves and sorting equipment separate crystals based on diameter, ensuring consistency in texture and flow. Uniformity matters not only for appearance but also for performance, as evenly sized crystals dissolve predictably and pack efficiently. Any crystals that fall outside the desired range are returned to earlier stages, where they are dissolved and recrystallized rather than discarded. In facilities producing refined white sugar, additional purification steps may be applied. Raw or lightly colored sugar can be dissolved again and passed through advanced filtration systems using activated carbon or ion exchange resins. These systems remove trace color compounds and impurities that remain after initial processing. The purified solution is then recrystallized, producing bright white crystals with exceptionally high purity. This extra refinement meets the strict standards required for food manufacturing and consumer markets. Throughout these finishing stages, quality control remains constant. Laboratory technicians collect samples at regular intervals, examining crystal size, moisture content, color, and purity. Specialized instruments measure reflectance and composition, ensuring that each batch meets regulatory and internal specifications. Any deviation triggers immediate adjustments, preventing large-scale inconsistencies. This continuous monitoring ensures that the sugar leaving the factory is safe, stable, and consistent. Once approved, the finished sugar is directed to storage or packaging. Large silos hold bulk quantities under controlled conditions, protecting the crystals from humidity and contamination. Automated packaging lines then measure precise amounts of sugar into bags of various sizes, from small household packages to large industrial sacks. High-speed machines fill, seal, and label each bag with accuracy, minimizing human handling and maintaining hygiene. The packaged sugar is stacked on pallets and moved to warehouses, where it awaits distribution. Forklifts and conveyor systems handle the movement efficiently, preparing shipments for regional and international transport. From here, sugar travels to supermarkets, bakeries, beverage producers, and countless other destinations, becoming an ingredient in everyday life. The final stage of sugar production reflects the culmination of every earlier decision, from farming practices to mechanical precision. Each crystal carries the result of careful drying, refining, inspection, and handling, ensuring it reaches consumers in perfect condition. What began as raw juice in a fibrous plant has now become a stable, uniform product, ready to dissolve quietly into food and drink, completing its journey from field to finished form.